Okay,
variations, but
I don't have a religious contention with the
oh
Big
yeah, yeah,
Bang
yeah.
model.
No,
Yeah.
that's yeah, yeah.
Like
We can
I
drop that if you
actually
want.
agree. Like the Christian apologists, like you said, they're the ones using the Big Bang model as like evidence for God. Like,
Right.
so it has nothing to do with that. But I mean, my biggest problem with it is that once I started reading about it, I was like, oh my gosh, like I've been told for years and years and years that we have so much evidence for the Big Bang. And then to like realize as I'm reading how incredibly weak, I did not know how weak the theory actually is. And so I mean, you know, starting out, I didn't know if I was going to be able to make a strong case against the Big Bang. But it was like, oh my gosh, like this is all basically myth and hypothetical entities. And I mean, now I just think, wow, I just really want people to know the truth about how weak it is. But I mean, how do you feel about it?
Um. So actually, let me back up by saying so. My background is in physics, but I'm not a cosmologist. So like I do mathematical physics, I do general relativity stuff and conformal geometry, things like that. So like while I probably know more about general relativity and the Big Bang than perhaps say like a I don't know, like a condensed matter physicist, it's not something like I'm not an astrophysicist. I don't analyze this kind of data. But anyway, so if I were to say it, so it seems like it's the most convincing model that we have, and it seems like it's there are features of the Big Bang that are unexplainable using any other model. The what it would be so it seems like a Big Bang model can kind of be argued. You could argue from it just from parsimony alone, in that if you want, there are other ways to explain different aspects. Like you could come up with a model that explains the cosmological microwave background. You could come up with a model that explains redshift. You could come up with a model that explains, other examples, what is it called? Like sorry, I'm just blanking on the word.
That's
Basically
okay.
what I'm saying is you come up with a whole bunch of models that explain the different things. Big Bang nucleosynthesis, for example, like the abundance of light elements. You come with models that explain these things in part, but I don't think that you could come up with a model that explains all of them at the same time. And so, just from like a parsimony perspective, it seems like that a Big Bang model seems whether it's complete or not is a different story, but it seems like it has the most power to. It's the simplest model that can explain the most things that we have available to us. Now, that's not to say that that it doesn't have its flaws, because I mean, as you've pointed out, and as I have talked about before, the Big Bang model, at least as currently described, seems to not particularly accurately predict lithium abundance, for example, at least as far as we can tell. And there are problems with like homogeneity on a large scale, which I'm sure then you can talk about inflation and things like that. So there are problems with it. But I think it's like a measure of, it's like a weighing game, right? Like you have to decide, like, do the predictions that we can make from a Big Bang model is the evidence in favor of the Big Bang sufficiently strong that we should be able to trust the predictions made by the Big Bang model? And I think in that case, I think the evidence comes out in favor, like as far as like the balance goes. That's my perspective on it. If evidence comes out tomorrow, if someone comes out tomorrow with a model that explains the CMB, explains the redshift, or like Hubble's law explains, light element abundance, things like that, that doesn't require universal expansion and doesn't have the same issues that the Big Bang does, great, I'd latch onto that, no problem. But there isn't such a thing. So
That's something, Sal used the analogy in in the debate, I believe, or maybe in just another conversation, but he said, you know, if we have like, if we're like looking for someone to pin a murder on, do we just grab any random person and say, well, we don't have anyone better. So until we have anyone better, you're guilty.
well, I think it would be like, I don't know. I don't think that the analogy is great, right? It'd be like, oh, well, we see your blood at the scene and you own the knife, but the camera showed somebody that doesn't look exactly like you. So like, then you'd put it in front of a trial and you would ask the jury, is the propon or is the evidence sufficient beyond a reasonable doubt? And if the jury says yes, if they weigh the evidence and they say that yes, the evidence is sufficient, then yeah, that's that's how our legal system works. It's also kind of how the scientific system works, right? Like models are cumulative. You start off with and I mean, I'm sure you know the history of the Big Bang. Like it started in like the 40s, maybe the 50s or whatever. And like they were making predictions that were like wildly inaccurate. And as we got more and more, not some of them were not wildly inaccurate, some of them were. As we got more and more data, as we collected better and better, dark matter came into the mix, then we saw accelerating expansion, things like that. The model got more and more fine-tuned. And so now we have, now our predictions are able to, are more likely to line up with what we observe. So, I mean, it just I think we can both agree it's not perfect, but I don't know why we would expect it to be.
Yeah, well, now and this is where I would like to hear your feedback about the debate. The reason is because what we came up with, I felt like, wow, like anybody who watches this, of course, I'm a layperson, so I'm very interested to hear what someone like you who actually has expertise and who doesn't seem like just a Big Bang zombie. Like I've watched enough of your videos to like believe that, you're an honest and critical thinker. And yeah, so I watched a lot of your videos, and then Danny also, gave you a high recommendation. So I was like, okay, like I feel like this is like someone who's not just going to be blind to the evidence. And I mean, to be honest, I feel like we absolutely killed the Big Bang in that debate. So I'm just wondering, like, after like the evidence that we presented, like, what did you think about the evidence we presented, especially like the evidence against expansion?
So it seemed like, and so I watched it and I was taking notes, and I'm like, look, and then I thought to myself, this isn't a formal debate. I don't need to take notes and have rebuttals prepared. So I deleted the file because I didn't want to like, come at you with like talking points. At this time, you said that, like, that just felt kind of dishonest and shitty. So like I'll just go off kind of what I remember. So so like it seemed like, and this is just the overall vibe that I got, is that there were a few studies, a few papers that were written that are I don't know what the word is, like not mainstream, or that they contradict the lambda CDM model. Fine. And it seemed like maybe 3 papers. I think there was that one that was published that was published recently from the JWST data that was mentioned. There was like that nice beautiful plot. There was a plot about there something about like the blurring effect of tired light. There was a paper that was referenced there about how actually there isn't a blurring effect, and then it looked like so those are the 2 ones that I remember most specifically. And so I looked into them, and and then there was also a paper by Eric Lerner, and like this is like basically anytime I see anything by Eric Lerner, I automatically dismiss it, because his argument. Thank you for the glasses, by the way. I do this thing where, because I'm a broke guy who lives in Europe, not broke, but I live in Europe. I'm a researcher. We don't get paid well. But anyway, so if somebody's sending me glasses, I have to say thank you. So first and foremost, I have a problem with Eric Lerner because his story hasn't changed since the 90s on how he feels about the Big Bang, despite like different evidences and interpretations and models that I've come up with. It's just he seems dogmatically opposed to the Big Bang, as opposed to just following his nose where the data goes. So like it just seems like that's, I mean, like I'm sure that he does some analysis, but it'd be like if you saw a paper by Richard Dawkins, you would probably immediately be like, wait a minute, I need to take what he says with a grain of salt, right? So that's kind of the that's kind of the feeling that I get with Eric Lerner. There was the paper that you mentioned, or I think Sal mentioned it, I guess, about the JWST is interesting, and I have some thoughts on that. I haven't read it in its entirety. I have some thoughts on that, but there was also this paper about there was some tired light discussion, and so my feeling is that it seemed like there were a few studies that were picked out amongst the dearth of studies that have been investigated that support the perspective you're coming from. And
Mm-hmm.
unfortunately, your opposition didn't bring the other studies that criticize the studies that you mentioned. So, I mean,
Mm-hmm.
like you guys definitely came off better because you guys came with papers, evidence, plots,
Mm-hmm.
charts. I think that your opposition probably underestimated you a little bit because they're like, oh, they're young Earth creationists. What do they know, right? I don't have to do any
Mm-hmm.
preparation. But for a debate, you should do your homework, right? So all I have to say is that like it seems like the things that are most pressing is an explanation of redshift and an explanation of the cosmic
Mm-hmm.
microwave background radiation. Both of those are like, those are widely regarded as kind of like the holy grails of Big Bang cosmology, if you will. And I don't think you guys addressed cosmic microwave background radiation, which I just like to hear what you have. Like they didn't ask about it, so you didn't have to. But the tired light thing, it seems like there's like I've looked into the paper that was talked or the paper that was talked about in the tired light thing, and it seems like it's just I haven't seen any convincing evidence for it. There's a lot of there are a lot of problems with the tired light model. One problem is that you have this defocusing thing, which I think one of your opposition mentioned, right?
Mm-hmm.
This defocusing thing. And I think Sal said that, oh, well, there's a model that you can come up with that involves electron plasmas that treats it like a transparent medium that can prevent the defocusing thing. But that's not the only issue with the tired light model. The other issue with the tired light model, or one of the other issues with the tired light model, is the time dilation problem. And I think that this was brought up by Sal. Maybe you brought it up.
Yeah.
But
Mm-hmm.
but like I've looked into this, and I found one paper that seems to suggest, and it's by this, or actually I found 3 papers all by the same author. That make the claim that like the supernova, the Type 1a supernova, and the gamma ray burst calculations, data analysis doesn't suggest time dilation. And I found like 6 papers by a dearth of authors that do the same analysis and come to the opposite conclusion. So it's really hard to say that that's like definitive evidence. I mean, like we typically don't argue by like consensus or by majority rules in science, but I didn't read all like 6 papers or whatever, but it just seems like I don't know who this other guy is. I think it was David Crawford. I haven't seen his work before, but
Yeah.
it seems like if he's the only one publishing on this and he's written so much about it, it seems like he has skin in the game. And so I'm just a little bit suspect is all. So I don't know. It seems like it's not nearly as cut and dried as it was made out to be.
Well,
did I say
are
it?
you also
Dearth doesn't mean
suspect about the people who built their lives and reputations on the Big Bang? Like, because that's the situation. Like, there's so many people that have like built their entire like careers on the Big Bang. So, are they also suspect?
So, sorry, I just misused the word dearths. I meant the opposite of dearth. An abundance of authors, not dearth. Yeah. So I get the feeling. And I understand the vibe. It's to an extent, yeah. Basically, but what I don't do is I don't look at, for example, if David Crawford had written one paper on this and then wrote a whole bunch of papers on other things, that would be one thing, because it means that he doesn't have a bone to pick. But it seems like this is what he's been doing. This is his whole thing. And when I go look at the author at like the scholarship of these other authors, they like study galaxy formation, or they go study or they study like neutrinos or whatever. And so it just seems like there's a class, like a subset of people who, for whatever reason, are contrarians. And by the way, another good example of this would be Mordechai Milgram. He's the modified Newtonian dynamics guy. He hates dark matter. And so, like, he spent the last 40 years just authoring paper after paper after paper on this subject. And I'm like, okay, well, if I see a paper by him, he's coming in with bias. And so when I see a single author doing that, it seems worse to me somehow than 4 or 5 different authors who have all written on different things, like talking about one thing once and then moving on to another thing. You know what I mean? That's the feeling that I'm getting. But I do understand the suspicion that you have. That is reasonable.
Yeah, so I I guess, I mean, and so I would really prefer to like go away from just like attacking the people and really think about like the ideas, like what
Yeah,
are
that's
the,
fine. That's fine.
because I mean, I put a list of names up on the screen, and actually there's like a couple hundred more who've now signed that open letter to cosmology, open letter for cosmology. And in that, it is scientists from all over the world expressing the problems with the Big Bang, and that, young scientists are told basically, like, are really taught to not question the Big Bang. But anyway, so, there, I, I, I can't argue about what certain people's motivations
Sure,
are. I
that's
don't
fine.
know what, their motivations are, but I mean, I guess I'd just like to evaluate are their ideas correct or incorrect?
Yeah, no,
And
I mean, and that's totally fair. Sorry.
I can't, and also I'm not like, I didn't really, study the part of it about like the time dilation and the plasma and the things involving the redshift, like alternative explanations for the redshift. That was more Sal's department.
Sure.
So my department that I was looking into was more looking at the problems with the Big Bang model. So I'm kind of interested to hear, like, what do you think, like, is the evidence for expansion? Because that's what we asked our opponents for, and that's what I looked for. I actually looked for evidence for expansion, and that's something that I could not find. So
yeah, go ahead.
yeah,
Sorry.
no, go ahead. I'd like to hear if you know of, like, what is the evidence that expansion is true?
So, and actually, you're not the first person to ask me this. And in a sense, even in principle, it can't be tested. It can't be measured directly, because where there's matter, where you like, let's say that you wanted to get out a ruler, right, and measure expansion, and let's say even you could even live for 1,000,000 years. Well, if there's matter present, the expansion won't happen, right? Expansion happens in the void of empty space, where there's no matter to gravitationally bind it together. So, in principle, it's not even measurable it's not even possible to directly measure expansion. Rather, what we think about, and this is, and by the way, I'm not associating with them. I'm just connecting it with context I've had. This is the kind of argument that, like, I talk with flat earthers a lot. And so this is the kind of trouble that I have explaining to them, because they'll ask for questions like direct evidence. Did somebody literally like get a ruler and measurement? And I'm like, no, but that's not how we do science in this day and age. Not everything is easily measurable directly, but instead, what we do is we think about, okay, let's imagine that the universe is expanding. What telltale signatures, what smoking guns would there be? And then we go out and look for those. So like one telltale signature would be redshift. That like, if like, I'm sure that you could agree that if the universe was expanding, we would expect to see redshift, right? I'm not saying that the universe necessarily is expanding, but that is a prediction that expansion makes. We would also expect to see time dilation. So if the universe were expanding, we would expect to see time dilation. And so like those are two pieces of evidence that would have to be observed in order for expansion to be happening. And so people go out and look, and depending on the papers that you read, they find it. So I'm not sure what kind of evidence you could. I mean, like, and we could I guess dig even deeper and ask for like what other consequences would we expect to see from expansion. But I'm not sure what other kind of evidence you would want to see.
Right. Well, okay. So the redshift, but you also, are you admitting that there could be an alternative explanation for the redshift?
Yeah. So any explanation for the redshift would also have to account for the observed time dilation. If you accept that that's been so. Assuming that we measure redshift and assuming that we measure like concordantly associated time dilation, any explanation for the redshift would have to equally account for the explanation of the time dilation, or at least you would need a new explanation for both.
Right.
But yeah, in principle,
I think
yes.
the time dilation, I feel like that's one that's in dispute, because like Sal brought evidence that the time dilation is showing non-expansion. You've cited sources that say that there is, so that's one I can't like call it. You know what I mean? Like, I don't know
that's fine.
What the right answer is on that.
Sure. But we definitely do agree that there is redshift, right?
Yes.
So the question is is then we need to so we need something. Well, okay. So one possible solution is that we just say, look, there's redshift and we don't know what causes it. And that is generally fine. Like for what it's worth, I get asked the question a lot, what made the Big Bang happen, or what caused the Big Bang? If the Big Bang really happened, how did it happen? I get asked that question a lot. And I just say, look, I don't know. I think that's like a fair answer. I think it's fair to say that that's an answer, because it's not like we have a model that predicts what should have happened, and then that model can or can't be tested. We just don't have anything that can tell us about that.
Mm-hmm.
And if it were the case that we just saw redshift happening and we didn't have a model that could explain it, or rather we could come up with a model that could explain it, but it made some obvious prediction that wasn't verified, or whatever, then maybe the answer is you just say, I don't know. And you just say, well, that model just isn't good, but we just don't have any other model. And that would be fine. But that doesn't seem to be the situation that we're in.
Okay. How so?
Well, I mean, the Big Bang was, maybe somebody mentioned in the comments that it was 1931 that Lemaitre wrote it down or talked about it for the first time. I don't know the history of this thing, but what's quite the perhaps very surprising thing is when you have a model that describes one phenomenon and then it makes a prediction and that prediction comes true for another phenomenon, right? So you might have, and correct me on the history, on the timeline if I'm getting it wrong, but my understanding is you have Hubble and co observing some sort of redshift, right? Not really understood.
Yep.
Then you have Lemaitre coming along and talking about a primordial atom, and I think you have Gamow in the 40s or something like that, talking about the CMB, and then you have a CMB detected in the 60s. And so, it's not often that you actually have theory leading experiment or theory leading observation in science. Usually it's often you find something funny and then you come up with an explanation for a post hoc. But this is really a genuine case of, we have a prediction that there is some sort of background radiation, right, that was then detected a decade and a half or 2 decades later. So that seems, that's the kind of thing that I would expect for a model that represents the universe we live in. Now, it could be that that it was just kind of a lucky guess, that's not actually the reason why the CMB was detected, and it's just a coincidence that this model that was wrong was predicted something that was right. But after a certain point, after we keep thinking about anisotropies in the CMB, for example, when we start making precision measurements based off of precision models, and they continue agreeing, at a certain point we have to say, well, does the incompleteness of one model mean that we have to throw away the predictive power of this model? And on that, I would say the answer seems to be no.
Yeah. Well, if first, Gamow, his prediction about the CMB was off by an order of magnitude. So although, we did find CMB, it wasn't according to what he predicted. And then, issues have arisen with the CMB that it hasn't followed the predictions completely. And I may not be able to describe the, exact details of that without looking at a source right now. But
sure, no, that's fine.
But the CMB hasn't been what we completely expected. It hasn't been isotropic or according to the expectation. And then you also have the axis of evil, and so there's issues with the CMB where I don't think it's a smoking gun for the Big Bang model. It's caused problems that, just like with the other things in the Big Bang model, when it doesn't fit predictions, things are made up and to fit to keep the theory alive. So I feel like that's what's happened with the CMB, is as it doesn't follow the predictions, then they just make up something else to account for it.
So I don't know the history here. And I heard the claim that Gamow's prediction was off by an order of magnitude. Fine, But also, do you know what year that was predicted in like I want to say it was 48, right?
I don't remember the exact year. I
Like
know they found it in 1965. They found the CMB.
Right.
Yeah.
I want to say Gemma wrote about it in like the 40s, but
Yeah.
So this is all to say, they presumably the idea of a microwave background radiation or of background radiation at all, like hypothetically, if the Big Bang did happen, whether you know the intricate details of the age of the universe or the composition of the universe or the fine details of the quantum mechanical interactions that are taking place, in the early universe, all those things. Regardless of those, we could reasonably expect that there would be a microwave or a background radiation. Now, so the idea itself is fine, and that Gamma predicted that idea that such a thing would exist. I think is more indicative than the fine details. I mean, it would have been great if the fine details were accurately predicted, but we also know that the size of the observable universe wasn't known at the time. The standard model, which is used to talk about discussions of how quarks and quarks they didn't even know about quarks, like the existence of quarks at the time. So the questions about how the primordial universe would have evolved and would have behaved, were completely unknown at the time. So perhaps it's not so surprising that his prediction that his numerical predictions were off. But I think a key point is that the idea that the seed of the idea is there, and it that core idea was correct. That there was a universe filling radiation background that should be there if the universe was at one point in time hot, dense, and small. And
right.
so
yeah,
and it's not like that those it's not like the the discovery or the invention, if you want to call it that, of quarks or the observing the size of our observable universe. It's not like those things were added on to fix the CMB predictions. Those were separate measurements done to separate measurements and observations and discoveries that just happened to focus the model building ability of cosmologists, right? So the standard model came about in the 50s and 60s and I guess 70s for completely unrelated reasons. But once you incorporate the standard model into your early universe, now you can start making better predictions as to what you would expect to happen because quantum mechanical effects start taking place. Once you know the size of the universe, and once you have measures as to how old you think the universe is because you're detecting light from such and such distance, well, now that can feed into your prediction of how hot the CMB should be. So it almost seems like that. The only two examples I can think of are dark energy and dark matter, right? Of things that are kind of added in ad hoc, and we can talk about those if you want. But it as far as the standard physics, like the standard model of particle physics, standard astronomy things like measuring of galaxies and things like that, those all seem kind of like they were added in just naturally, not to fix anything, but just because that's what we observed. If that makes sense.
Okay. Yeah, we might. We can talk about that. I just want to kind of close up on the CMB before
you're good. You're good. That's fine.
So I just, I'm happy to grant the Big Bang a point for CMB. And if you notice on the debate, I put the good predictions.
That's right. That's right.
That the Big Bang made and the failed ones, and I put CMB on the, good predictions.
With a question mark, I think.
With a caveat.
Yeah.
Okay, so I'm happy to grant that, but then we got to talk about the failed predictions as well, and say at what point do we say, okay, the model is no good? How many failed predictions does it take before we say the model is no good? And then we can, if you want to respond to that, you can, and then we can talk about dark matter, dark energy. Although I think dark energy is the more important one to talk about because I'd like to hear what your response is to what I said in the
discussion in the CMB about the dark matter. Dark matter is a red herring. There's some discussion of dark matter showing up in CMB anisotropies, but that's really, really minute, minutia stuff. So yeah, sorry, what was I responding to? You just mentioned
CMB,
something.
The CMB.
Yeah. So so I think we just agree. At least to some extent, there was a prediction that was made, and perhaps with some caveats. Yes, the CMB
Yes.
seems to be in favor of the of the Big Bang model. Now, and for what it's worth, I actually think, and again, I could be wrong, but historically, the Big Bang model wasn't accepted until the CMB was discovered, because that was kind of viewed as like a smoking gun, right?
Yes.
So perhaps that's why it's used as such a strong piece of evidence, because that really was what convinced people, right? This is tangential, and it's just interesting. I made a video on it a few weeks ago, maybe a month or two ago by now. Have you heard of the neutrino background?
Yes, but I wouldn't be able to like speak intelligently about it. Yeah.
So this is just something, if you don't mind, I just want to talk about it because it's cool.
Sure.
So, and this just has to do with people that I know. So, neutrinos are really hard to detect, like really, really hard to detect. And especially if the Big Bang model is true, the neutrinos that we can detect now are very high energy. The neutrinos that we would be needing to detect are very low energy, which makes them even harder to detect. So what you can do is you can look at the CMB power spectra, and you can like try to analyze like what if there was a neutrino background, what would it look like, and would there be anything missing from it, and so on and so forth. And so you can do that. That's cool. And you actually by looking at the cosmic microwave background radiation, one of the conclusions that you can come to is that there has to be exactly 3 neutrinos in our universe, 3 different types of neutrinos. Sorry, somebody's asking in the comments, what's the CMB? Cosmic microwave background. It's the so-called smoking gun of the Big Bang. Anyway, so one of the predictions that you can make just from looking at like the power spectra, and it's complicated, and I haven't read the paper in its entirety, but is that there are exactly 3 types of neutrinos. Now, this doesn't involve the standard model at all. Like the types of calculations that you could do, the models that you put in to try to predict this, you put in n neutrinos, and then you just do the math and you figure out how many neutrinos does the CMB tell us there should be. And you find that there's 3, and then you go look in particle physics, and we've only found 3. So that just seems amazing to me. And even more, and this is even though we haven't actually detected a neutrino background. And the reason why I brought this up at all is because there's actually an experiment, like a detector, that one hopes is going to be able to make predictions or actually detect this neutrino background, like directly detect the neutrinos for the first time. I think it's supposed to go online this year. So that's just exciting to me, and I wanted to talk about it.
Cool.
And like the science behind the detect, like I don't usually care about experiments at all. Like I'm not an experimentalist. I did that in my undergrad. I thought it was terrible, but the sort of like ultra high precision detection that they want to do and that they plan to do, and I looked through the paper, and they actually like it seems reasonable that they can do it, is it seems plausible, and I'm really excited to see what comes out of it, because that would be, it would not only would it be even more of a smoking gun for the Big Bang. If the Big Bang is true, it would let us peer even further back in time, further back than 380,000 years or something like that, because neutrinos decoupled 1 second after the Big Bang rather than 380,000 years. So that's just something that's really cool. But anyway, sorry for the
detour
distraction. Yeah, detour. 1 moment. I think my phone unplugged.
That's fine. Smoking gun, I'm happy to give it a point, but if there were no alternative explanations for it, then maybe it would be a smoking gun. But it's, there are other ways to explain it. And in fact, because of the axis of evil, we kind of have a good reason to think that we may not be getting that all the way from, basically the distant universe.
So I haven't, and I don't remember if you mentioned this, but like, what are the other possible explanations? I just don't know them.
Okay, yeah, and I did read this in the debate, so I'm just going to read this.
Sure.
It's this is from Eric Lerner. I know you're not happy with him, but this is
it's fine.
He offers this as an alternative explanation. He says that there's repeatedly in the past, and as pointed out, and again. Section 4.2, the energy needed to account for the microwave background is comparable to the energy that would have been released by the production of ordinary stars of the known amount of helium, as predicted by the galactic origin of light elements. That's his idea. And he says, the present author, along with others, proposed that the CMB is a radio fog permeating the present-day universe, not some ghost of a long ago Big Bang.
So, and I just don't know how this works. So his proposition is that helium, so it relies on like a different type of nucleosynthesis, right? Like where you have helium formation rather than like in galaxies.
Well, and remember that I don't, he's not, he doesn't think that there was a beginning of the universe. Like, I mean, and I know now people are saying the Big Bang wasn't the beginning, whatever, but basically he doesn't accept the Big Bang model at all. So he has a different idea about how matter and stars and everything formed. Although I am not, like, I did not really investigate his model. So
sure. So I mean, I'd have to think about it, like, because because there, there's questions of like, well, how did I just can't comment on it. Oh, there was one other thing I wanted to add about the CMB, which is, and I was just doing some cursory Googling while I was walking. When was I reading about this? I was walking home from the store yesterday. Because walkable cities are great. By the way, I don't know where you live. I live in Central Europe, and I live in a very walkable city, and it's excellent. So would highly recommend. Cool. I was doing some reading, and it seems like it's actually not even, like, it's in contention whether the axis of evil is even a real thing. Because I found a few papers that suggest that, like, that the significance of the detection is too small. So I'm not making any claims about that, but this is something I didn't know about, so I looked into it, and it looks like that I can find convincing arguments on both sides, seemingly. So I'm not throwing it out. I'm just saying, like, I don't know.
Yeah, well, my understanding of it is that from 3 different satellite experiments that we've done, like experiments with 3 different satellites, it has been observed. And I know that there are objections to it, but it's like kind of something that they wish would go away, but it really hasn't. But I mean, I acknowledge your point that there is opposition to it, and so yeah, I mean, we can leave that as an unknown.
Yeah, and I mean, like, so I'm not arguing. So for what it's worth, I'm not arguing for any one particular model of the Big Bang. What I'm suggesting is that it seems like, to me anyway, the preponderance of evidence suggests that the universe is expanding and has been expanding. Now, causes and the details of what's driving the expansion, or how quickly it's been expanding, or the rate of expansion at in different epochs, or all of these things, it seems like that if those. Or the homogeneity, all of these sorts of things. If these things change as new information comes about, as new models are developed, that's not like a nail in the coffin for me, because to me that just seems like it's how science typically operates. Like we have kind of like a model that then gets improved upon as time goes on. While I think that while the lambda CDM model seems to be pretty good, if something comes out tomorrow and says, hey, this problem is there's this thing that is contradictory to such and such a thing, or it's a nail in the coffin, I'd be like, okay, well, what alternatives are there? How can we build a model that gets around this, that excludes this supposed, like, I'm happy to take on different models. Hell, I'd even be happy, like, if it turns out that, like, there is a consistent model that someone can come up with that leads to it, like, an eternal universe, fine. Like, if that's the case, like, if you come up with like a more parsimonious model that can explain all of these things, cool. Like that, I'm fine with that. It just doesn't seem like it's happened. That's all.
Well, now you're saying the preponderance of evidence is for expansion, but I actually do think that we already have what you're talking about, like something that came out that's totally against expansion. And that was what we put forward with the observations of these new galaxies. And of course, we didn't have time to go in depth in the debate because we were very limited on time. But I think that evidence is there that is flatly showing that the expansion model is wrong. So did you have a chance to look at that?
Yeah, I did. Yeah. It was like you're talking about that one that has like that lovely graph, right?
Yes. Yep.
So my understanding, and I could be getting this wrong because I didn't read through the whole paper, but my understanding is that It was angular size versus redshift, and the model that they were using to predict angular size was based off of predicted. So what I think was happening, and again, correct me if I'm wrong, but what I think was happening is that they were assuming galactic formation models that, like current galactic formation models, to predict sizes of the galaxies that we observe, and because we're seeing galaxies that are different in size than what we would expect, you have this contradiction. But, and again, I could be wrong, but it seemed like the assumption was made in that document that the galaxy formation models we have are correct, right?
Well, they're assuming that, like, okay, because like they're taking observations of galaxies in local galaxies, basically, like,
Right.
so that you're right that they are assuming that, you know, if we see an elliptical galaxy or a spiral galaxy at this far distance, that it will be comparable to the galaxies that are in our local universe.
Right. But so it seems like because it's not as simple as if Big Bang, then this, if not Big Bang, then that. It's if Big Bang, and if galaxies nearby are similar to galaxies far away, then this. And if not both of those things, or if not one of those things, then this. Like you see what I'm saying? Like it doesn't seem like it eliminates both. It doesn't seem like it fixes it to one variable that's changing, you know?
Well, this is where it's good to have a physicist, okay? Because, you know, you're going to know more about this than I am. But so is there a limit? Like, wouldn't there be a limit to how many stars you could fit, like, in a condensed space without it, like, like, wouldn't there be like a, where would the limit be for like how massive a small like galaxy could be? Do you know what I mean? Like, because I mean, the reason I'm asking is because like
massive a small galaxy could be. Yeah, go ahead.
No, but I mean, I don't know if I'm expressing this. And then it not like collapse in.
So I'm not an astrophysicist. I'm going to say tentatively, I don't see why if they're orbiting fast enough. So stars are generally really far away from each other, right? So it's not like a star itself is way more dense, and stars are not like the sun would float, right? If you put it in a bathtub, the sun would float. It's not very dense. But because the distance between stars is so great, it's not like that there's any risk of like a black hole forming if you bring them like if you brought all the stars in the Milky Way, if you halved the distance between all the stars in the Milky Way, then it wouldn't like collapse into a black hole. They would just orbit each other faster. It's because like the distances are still massive. They're just slightly less massive. So I don't think, I mean, like, yes, you probably couldn't fit like 100 stars in our solar system, but I don't think that's what we're talking. I don't think we're talking about like that scale of like condensed stellar objects, right?
Yeah, that's the issue, is that you know, we're seeing these galaxies that are elliptical and spiral galaxies, and yeah, we can't really know you know, if they are the same size as the galaxies in the local universe. But because, you know, if we calculate, if we add in the optical illusion and calculate for expansion, then those elliptical and spiral galaxies that we're looking at, they have to be way more massive, way more dense, way smaller, like hundreds of times smaller and more dense than the galaxies in the local universe. But
So,
if we just say non-expanding model, and we just, you know, take it as the redshift is there's a linear relationship to distance, and we don't have to make the expansion calculation, then those galaxies that we're looking at are comparable to the galaxies in the local universe.
I guess so. I guess the and I've had. Do you know who VOR is? Voice of Reason.
No.
Okay, maybe I don't know if he has a YouTube channel, but he has like, however many millions of followers on here. I think he's a young Earth creationist. But
Oh, really?
I've had a discussion with him about this, and I think and again, I'm not an astrophysicist. There's actually a lovely person on TikTok who's a PhD student in astrophysics. She studies galaxy formation. Anyway, so on a lot of these questions, like this is directly her specialty, so I would defer to her. But it sounds like from the times I've talked to her, it sounds like just our knowledge of what galaxies were like in the early universe is like very, very small, and it's basically based on simulations because generally these are not things that we can observe happening. So all we can observe happening is stages of galaxies, or galaxies in potentially different stages of their lifetime, and there are a few cases where we can observe galaxies like mid collision, right? So like the whole business of what galaxies look like over time, I think is just like so poorly understood, which is why it's such a big field right now. It's so poorly understood. It just seems it seems hasty to make broad assumptions about it, I guess.
Yeah, well, I mean, but the standard model has been making broad assumptions about it for a long time, and they've been wrong again and again, right? Like over the years, they've been wrong. This is many, like the failed predictions of the Big Bang are, a lot of them are related to galaxy formation.
Well,
right.
Right. So the question is what's really wrong here? Is it our galaxy formation models or is it the Big Bang model? And so you need to come up with a way of distinguishing between the two. So what we can do is we can look at predictions that we can try to find predictions of these models that are separate from each other, right? So the CMB, and I know we just talked about this, but I'm just using this as an example. The CMB doesn't have anything to do with galaxy formation, right? Like you can make that prediction, right. And whether we know anything about galaxy formation or not, it's independent. I don't know, and I'm just not well versed on this, but I imagine that there might be some predictions that you could make with our current galaxy formation that is independent of structure formation and Big Bang cosmology, but I just don't know if those I don't know if we've tested our galaxy formation models in places where we'd like to use them to understand the history of our universe. So it seems like it's a really hard thing to untangle, and in the places where we can separate them, where we can test the Big Bang separate from galaxy formation, it seems like that those predictions seem to be good, which suggests to me that the problems are not in the Big Bang model, but in the galaxy formation, because it's just in our galaxy formation. It's just in places where galaxy formation models are involved that we go wrong. You heard, I'm sure you heard the news about those 6 new massive galaxies that were found, however many weeks ago, whatever.
Yes.
Again, and I saw half a dozen videos or a dozen videos about this means the Big Bang's wrong, but then I went and I spoke to astrophysicists. Well, I spoke to 2 astrophysicists anyway, and I asked, well, okay, what can you tell me about the galaxy formation models at that time? And they said, nothing. We don't know anything. So I don't know why we're assuming that what we had already worked.
Yeah, but there's actually 2 different issues here that related to the galaxies. One is about galaxy formation, right? And so, okay, I can accept that the Big Bang, okay, they were wrong about galaxy formation, but expansion and the Big Bang could still be correct, right? And we just don't know how the galaxies formed.
Sure.
But one of the main arguments that we're making in that debate is that it's not just that galaxy formation is a problem. It's also that it contradicts expansion. Like what we're seeing with the galaxies is contradicting expansion. So that definitely is a problem. And it's also a problem for the Big Bang model if there's no possible way to account for galaxy formation within the model. So like if the Big Bang model, like, okay, it's fine to say, yeah, we don't know. But if we can say, we do know that there's no possible way
Right.
that galaxies could form within the Big Bang model, then, and that may be the point that we're at right now, because we're looking back at, 250 million years after the supposed Big Bang, and there's galaxies there. So how could that possibly fit in the model? If we can't find a possible way, then it might be time to scrap the model, right?
Yeah, no. So you're right. I mean, like it. I don't know how often you do debate stuff. It's an
That was
addiction
my
for me.
first formal debate. Yeah.
So I don't do I've never done a formal debate. I just like have conversations with like flat earthers and religious types, and anyway. So and sometimes politics, but that got me banned. So that's why I'm on my alt account. It seems like so from what I've heard, and I've talked to a few people. There's actually one person maybe in the chat, Chaos Nixie. I'm not going to bring him on, but he's a good dude. He's an astronomer, astrophysicist maybe. And it seems like that sorry, I just need to collect my thoughts.
It's fine.
So just as a possibility, one thing that we don't know about galaxy formation is, do the galaxies come first? Do the supermassive black holes come first? Do they form together? Right? That's something that's still an open question. And so there are some thoughts that, well, perhaps these supermassive black holes act as seeds for galaxies and then galaxies form around them. That's one possibility. And then there's the question of, well, okay, do we have ways to explain how these supermassive black holes could have formed so quickly? And so there have been some models that were put forward. I made a video on this. This is the only reason I know about this. By the way, one of the best things that I have ADHD, so if I digress, please forgive me. But one of the best things of starting this TikTok account and making videos is like, I've had to relearn and teach myself a lot of physics that isn't directly in the area that I work on. Okay. So like this is like general relativity is the direct area I work in, but like cosmology is a little bit of a tangent off of that, for example. Like quantum field theory is a little bit of a tangent off. So like it's been a delight to like have to force myself to learn about these things that are slightly tangentially related or slightly out of left field for me. But anyway, there's been a few proposals of things called black hole stars, which is basically a type of like quasi-stellar object that is hypothesized or predicted to allow for the creation of high mass, like not just stellar mass, but like high mass, more than 100 or 1,000 solar masses in mass black holes quickly over the course of like 5 to 10 million years, which is really remarkable if we think that the supermassive black holes form very quickly. So this is like an exciting thing that people are actually out there looking for. We're looking to see, do these things that are called black hole stars, do they actually exist? Because if they do exist, that would be an explanation as to how these black holes form so quickly. If they don't exist, well then maybe that's a point against the model, right? So there's to say that it's settled science, I don't think that it is yet. I think that it's an exciting time to be in the science, though, because there's a lot of things that are, have to be explained, which is what scientists get excited about, right?
Yeah. Yeah, I watched your video about how the black hole thing may contradict expansion. Like, is that...
which one?
Well, you have a video talking... I mean, I didn't fully understand it, but it was something about how some of our black hole observations may be contradicting they don't go well with the expansion model.
I
you don't
make
remember
a video every day. I just don't remember. I'm sorry.
That's okay. Maybe I could be misunderstanding it too. So
no. So this isn't just you misunderstanding. When I first made my account, I don't know who my target audience is. I still don't know, but I found that my videos are often far too technical for just about anybody. I don't know why I do that, but half my comments are usually, I don't understand this, but I like what I hear. So I promise it's not just you.
Okay. Well, Yeah, but like, so I think there's evidence that the galaxy stuff is contradicting expansion. But also, we can go to the dark energy thing,
Yeah,
because
sure.
I also think that is actually, we should use that as evidence against expansion.
Sure. So we can, just to get ahead of the weeds. I don't know. Is that a phrase?
Okay.
Get ahead of there's a phrase like to get ahead of it. So there's this thing that gets brought up a lot, how like dark energy is like the worst prediction ever made, like it's off by 120 orders of magnitude or something. I've looked into that claim, and I've actually looked into the calculations, and like I don't know who first propagated that idea, but it's like a really, really shitty idea, because the calculation that they did, sorry for swearing, by the way.
That's okay.
You're not going to get banned. I probably, but the calculation that was done is like really a rudimentary calculation, and it's just like based off of the assumption that our knowledge of quantum field theory is perfect, and like that there's nothing else to be found, and that there will never be anything else, and everything that we know about quantum field theory will exactly match up with general relativity, which is just like, it's an absurd idea to even consider that. Like, why would we use something that we know doesn't behave well in areas of high space-time curvature to explain something that happens as a result of space-time? It just seems like it seems like such a, I don't know, out of left field red herring, I guess. Like, it's completely unrelated. You might hope that you can make some sort of prediction from that, but I don't think we're nearly there yet, where we can properly use quantum field theory to try to make predictions, because we don't have a theory of quantum gravity. Like, it's just, there's just nothing there. So that, I don't know, that 120 orders of magnitude thing, like it just seems like not a useful claim.
Right, but I mean, what did you think about what I brought up in the debate about how we came up with dark energy? And it's based, like, we had to come up with that in order to keep expansion alive. Like, we otherwise, like, that if we would have just left the calculation alone, like, do you know what I'm talking about?
Yeah. So,
okay.
And I might be biased here. So, like, I work in general relativity. I work with Einstein's field equations. That's like my, to an extent, my bread and butter. And so one of the things that is often mentioned is like, well, Einstein, what's the history that Einstein added the cosmological constant and then got rid of it, and he called getting rid of it, or he called adding it his greatest mistake or something like that, right? And then he got rid of it or whatever. So like, this whole business of a cosmological constant, the way I see it is that there's not a good reason to not have one. So typically the way I like to think about laws of motion, which the Einstein field equations are, is if a term can be there, you should treat it as if it is. This is what happens in quantum physics a lot too. Like, typically you assume that there are terms there, like terms in some sort of formula, unless you have reason to think that that term should be zero. In this case, the cosmological constant is just a term that can be there. It doesn't make Einstein's field equations inconsistent or anything. It's just a term that's allowed to be there. So it just seems natural that it would be there. And I would have to be convinced as to a reason why it shouldn't be, rather than why it should be. So I think that people up until, I guess, the 90s were kind of just taking Einstein at his word that this is just not how it is. But they really were just mistaken. And Einstein was right that the term should be there because it's a natural thing to have there. Unless you have a reason why it shouldn't be there, I don't know why you would discount it to begin with. And I don't think Einstein had a reason to think that it shouldn't be there. So this is just my bias coming through. I work in, like, the general relativity that I do is not the general relativity of our universe typically, but it's still related. And so I work with cosmological constants that are negative typically, which is not what we see. We see a positive cosmological constant, but it just seems like, I don't know, why shouldn't it be there, right?
Well, I mean, but let's take the focus off the term and then why it was inserted. Why was it put back? Because I think that's the issue. Because what happened is that Adam Rees was doing the supernova. He had a great experiment going on with supernova observations, right? But the issue was, and this is what he said in his Nobel lecture, he said, we had to account for expansion. So we put in a K correction. And he said when he did that, his calculations, his computer basically showed that the universe had a negative mass. Okay.
So
and
when
then,
you say K, sorry for interrupting, just for clarity,
No,
because
go
when
ahead.
you say K correction, is that referring to like spatial curvature?
That's for the
Because like
physicists.
I saw
don't
that and
know.
I wasn't sure what he was referring to. But anyway, continue.
Yeah, well, actually, he said astronomers will know this term by K correction. Physicists will
Okay.
know it by a different term. So
Oh,
he,
okay.
he
Well,
actually,
so I
so
don't know.
maybe but so look, I can't get into the weeds about the math. I only know why he said he did it to account for the expansion of space. And when he accounted for the expansion of space, that caused the whole thing to show that the universe had a negative mass. And so the
Yeah.
only way to fix that was with coming up with some kind of force that could accelerate the expansion of the universe. So that's where the idea of dark energy came from. But my point in the debate was that, look, if we stop assuming that the universe is expanding, then we don't have to make up dark energy. Like the universe doesn't have a negative mass. Like if you just don't think that space is expanding, then everything's fine. Like your observations are great. It's this problem of assuming expansion that's causing us to come up with the hypothetical entity of dark energy.
So the way I see it is like this is a historical accident, right? Because the standard Einstein field equations up until I suppose the 90s, I think it was the late 90s, maybe the early 2000s, is you had a cosmological constant of zero, and that's just what everybody did. But that's just because Einstein made what I would call now a mistake. He was trying to, figure out something that describes our universe. But like, had Einstein never taken that term away, there would have never been any question of, is the universe, like, is there an expansion or whatever? Or like what I'm getting at is that it seems like the only reason it seems surprising to add back in dark energy, which by the way, I think is a terrible name for it. I think we can just call it a cosmological constant and be done with it. But the only reason it's surprising to have something mysterious called dark energy is because we thought that there was no cosmological constant. But the only reason we thought that was because Einstein took it away from his equations in the 30s, right?
Yeah, but shouldn't math correspond to reality? What I mean is like, the cosmological constant is an anti-gravity force, but we actually have no idea if there is such a thing. So like it maybe works with the math, but does it work in reality?
Well,
So in reality, why would we think that there's an anti-gravity force?
So part of this gets down to kind of like fundamental epistemology is not the right word. Fundamental, I don't know. There's a philosophy word that Danny would know, but it kind of gets down to like why is the universe described the way it is? So like you might ask the question. Thank you, Misty. I don't know who that was for, but thank you regardless. You might ask the question, well, why do we have to add in Heisenberg's uncertainty principle? That we don't see that happening in everyday life, so why do we have to add it in? Well, it's allowed, so maybe we should consider it. Well, so I guess what I'm getting at is that like we can't expect that our reality will always be as we expect it to be, if that makes sense. So like, yes, we don't see apples falling up, but we also don't live at a scale that is the size of galactic clusters, right? Just like how we don't see, and to use a terrible analogy because it's not quite true, but we don't see baseballs popping in and out of existence. But that's because we don't live at a scale of atoms. So, just because we don't have this this intuition or we don't have this everyday experience, I don't think means that we should necessarily like exclude it from the possibility of how our universe works.
Right, but if our scientific observations are like, what I mean is if adding in an anti-gravity force is like only necessary because of our faulty assumption, then shouldn't we just take away the assumption rather than like having to like invent an entity?
Well, I guess what I don't think, I think I just didn't express myself well.
Okay.
The way that you're phrasing it sounds like it's something that we're adding in. But like it could just be that this is something that should have always been there to begin with, that we just never kind of really thought about because we don't experience it on an everyday life. But it, like you can have you like hypothetically you could just investigate how a universe would look if we had a negative cosmological constant, and those universes, they could have life, they could have planets, no problem. And you could investigate what happens if you have a universe with zero cosmological constant or positive cosmological constant. And so all I'm getting at is like it doesn't seem like this is something that we should have defaulted to not having and then added it in later. It should have just been like something that we should have just considered as a possibility from the beginning, and use and see which of those values, positive, negative, or zero, agree with observation. And what we would find is like, yeah, if we have a positive cosmological constant, we do see that it matches up with observation. And so we should have, like, that's just what we should have started with to begin with.
But my contention is that it doesn't match up with observation.
But wasn't the point that Reese said?
What's that?
Wasn't it that what Reese said is that he was able to make his observations line up when he added when he added dark energy?
But only because it didn't match up with his observations. It matched up with his assumption, the calculation put in because of expansion. Okay, so like what I mean is if he just took his supernova observations and like just, did whatever with the supernova observations, he wouldn't need dark energy. Okay.
So, I mean,
but the problem is that he believed in expansion as I'm sure he was taught. So he needed to fit with the expansion. But if we say no, there is no expansion, then we don't need dark energy.
So so presumably, and I didn't look into what he's actually won the Nobel Prize for, but I presume it's for measurements of type 1a supernovas and observing like accelerating recession velocities or something like that.
It was
for accelerating
for the acceleration of the universe, for observing the acceleration of the universe. Yeah.
Right. So really what he detected was redshifts, right? And so the question is okay, he detects redshifts. Well, he could have just said, all right, I see these redshifts, but that's not a good paper. So you don't write a paper about just detecting something. You come up with an explanation for why that thing is there. It turns out the explanation that he had wasn't quite right. Or rather, the explanation that he had learned earlier, that there was like a slowing acceleration, right? Because that was what the model was prior to the 90s. A slowing acceleration didn't actually, a slowing expansion didn't actually fit the data that he collected. So he's like, well, wait a minute, that's not right. What if I do this? And then he proposed this new model where he has this thing where he adds dark energy, or what I would call the cosmological constant, and now it matches the data. So it's more that like yes, he added in an assumption, but this is kind of like what we do in science. We come up with a model and see if it matches the data, right? So that's like the whole game. If he had just published look, I have these increasing redshifts, that's not really science. That's just like posting a data set,
Yeah, but the whole problem is the starting assumption of expansion. And, so like there really isn't. I looked for this, okay? And maybe you can tell me why we assume expansion, but I could not find a scientific reason.
That's why.
What's that?
It's just redshift. It's redshift, right. And redshift and time dilation in the CMB. Like those are the primary reasons why that's like the assumed, because we don't really have a good explanation for those things otherwise.
Yeah, but even Hubble is the one who discovered. I mean, he's the one who like did the work on the redshift to show that it has a correlation with distance, right? And in his book, he says, he says, look, he discusses the different things that it could mean. And he says, okay, it could mean that there's velocity here, but we can't accept that because that would mean that we're in a favored location in the universe. Okay. And he says, he talks about the proposal of expansion, but he says there's no reason to assume expansion except to keep us out of that favored location. Okay. And then he says his favored one is that there's another explanation for redshift. So
Like Zwicky's tired light.
He suggested that, yeah, but he wasn't sure. He kind of talked about some various ideas, but basically what I'm saying is the Hubble constant, it can be totally true, without the Hubble law can be true without us assuming that means expansion. And there still isn't, as far as I understand, a scientific reason to believe that the redshift is expansion.
Well, sorry, and I just want to back up to the thing that you're saying about Hubble. So, and maybe I think I just misunderstood. So you said that he rejected the expansion because he didn't think that we were in a favored position in the universe?
No.
Because he
I'm sorry. Yeah. Okay. It might take me a few minutes to explain this properly. Good. Okay, so the first assumption that we would make when we see redshift is that things are moving away, that it actually is velocity, right?
Right.
That things are actually moving away from us. Okay. Right. But he said, we can't accept that everything is moving away from us just as a straight velocity. We can't accept that because that would put Earth at the center of the universe. Okay. So he can't accept the velocity thing. And he says it could be possible that it's expanding space, and that would solve that problem. That would make it so that we weren't in a favored location. Right. Okay. Right. So, but he also didn't like expansion because he said there's no reason, there's no scientific reason to basically accept this idea of expanding space. Right. So, anyway, so that's the point is I still don't, as far as I could find, there is no reason to accept that the redshift equals expansion of space. So
perhaps an analogy, it seems to me that this is just an issue of, well, not an issue. That's condescending. Sorry, I try to come off well, but I don't know how I'm coming off. But so it seems to me like this is I guess you disagree on what would constitute evidence. So are you familiar with the Rutherford experiments for the discovery of the structure of an atom in the early 1900s or maybe late 1800s?
No.
So the way the story goes is that there were all of these we knew atoms existed or something like atoms, some indivisible elemental thing from the 1850s, I want to say, from the periodic table guy. And the question is what are atoms made out of? And we had discovered electrons because you can shoot electrons off of things pretty easily. But we didn't really know how atoms worked. Where's the positive charge? Because if you know electrons are in atoms, but how are the positive charges distributed? So one model was the plum pudding model, where you have which is really funny, which is just it's a pudding of positive charge that the electrons are kind of just placed in like raisins. And so that's one possibility, that there's just a jelly of positive charge that the electrons live in, and that's what an atom is. Then there's another model, which we recognize today as correct, where you have a small, tiny nucleus of positive charge, and the electrons go around it, right? So the kind of the nail in the coffin for the plum pudding model, and the best evidence at the time anyway for the atomic theory, the nucleus model anyway, was when Rutherford and collaborators and grad students basically shot radiation at gold foil. So they had a really thin piece of gold, and they shot atoms at it. And most of the time the atoms would just the radiation would just pass straight through. And so but sometimes, very, very sometimes, very rarely, the radiation would just bounce back straight backwards. And so they took that to mean, well, there must be a really, really tiny dense thing in the middle. And when the radiation hits that dense thing, it bounces back. But most of the time it misses, and that's why it passes through. But they didn't observe the nucleus. They didn't directly detect it. They came up, they found they did an experiment whose results would be predicted by a small dense nucleus in the center of an atom surrounded by electrons. But, and the scientific community is yeah, that's really convincing evidence that atoms have this structure where you have a dense nucleus and you have an electron cloud around it. And that seems like that seems reasonable, right? Because it's not like the rest. It's not like the scientific community said, well, maybe that happened for another reason. Like, no, we have this experiment that we conduct, and then kind of the obvious consequence of this experiment, or the obvious prediction of this experiment, is that things will bounce off of the hard, dense nucleus. And so, but that it doesn't have to be that. There could have been some other reason that we haven't thought of that explains it, but that's not how we really we still treat it as good evidence, even though hypothetically you could imagine that there's some other explanation that we haven't thought of. So I kind of see the expansion the same way. Like, there isn't, like, you're right, Hubble's first explanation that, everything's just literally moving away from us would be the first obvious explanation. But then you run into issues of, we're in a special place, which I don't know how you feel about that, but that kind of goes against, like, the, what is not the anthropic principle, the cosmological principle, something like that. It goes against one of, like, kind of the underlying assumptions of building. So then what's the next most obvious thing? Well, universal expansion. That's the next obvious possible explanation for why this could be the case. And then you would say, well, okay, well, it's as good a guess as any. Let's test it. And then you go and you do a test, and that makes a remarkable prediction, cosmic microwave background. So it just seems homogeneity and isotropy. So thank you. So it seems like the expansion is the same type of evidence for redshift as atomic nuclei is for gold, or is for radiation particles bouncing off of gold foil. Like, those seem like analogous. And I don't think people would make the same argument about the atomic nuclei. I don't think they would say, well, it's not actually evidence for atomic nuclei. Like, no, it is. It's just a different area, so it's less contestable.
Right. But I mean, the redshift, we acknowledge, could also be something else, like the suggestion that it's caused by plasma. And there is a correlation with distance, but it doesn't mean expansion. So there is an alternative explanation that I think, it can work better with the data, because we have so many failed predictions with regard to expansion. So, like, the cosmic microwave background, okay, that, we grant that as a good prediction for the Big Bang. But then we have, contradictions with the homogeneity and, isotropy in the universe. Like, so, and so, like, there's many failed predictions with regard to that. Like, so, like, at what point do we say, okay, I listed the failed predictions, and, like, it's like, at what point, how many predictions would it take? Like, we've showed that the universe isn't this homogeneous place that was expected. There's large scale structures and different things.
We should talk about that, because we haven't yet. But that's something that we should talk about. Yeah. Continue. Sorry.
No, but I mean, how many failed predictions would it take for expansion?
I think that you would really need, like, basically one, right? But it has to be, like, uncontestable.
Mm-hmm.
Right? So like, you have to find, so there's a difference between, I can't come up with a good analogy, so I'll just say it directly. There's a difference between the Big Bang makes an incorrect prediction here, and the Big Bang is fundamentally incompatible with this observation, right? Mm-hmm. Because the former can be corrected. Oh, maybe we didn't properly understand galaxy formation, or maybe we didn't have a good model of particle physics to explain lithium composition, things like that, right?
Right.
But that's very different from saying, we actually observe it contracting. That means that expansion can't be happening, right? So for example, if we saw, like, if you made the expansion hypothesis and then you saw actually everything's blue shifting, that's actually incompatible. Like they're mutually contradictory. The difference, right, though, is that it's not mutually contradictory to say that there is a failed prediction, because a Big Bang, a scientific theory is a collection of ideas, right? It's a collection of models and laws and relationships, and all kind of tied together. And so, just like, never mind, not going to bring that up. So it's not enough to say that one prediction is false because you have to untie the whole web, right? One prediction being false might mean that that connection needs to be tweaked, or that connection is wrong. But the whole conception of the thing, to throw that whole thing away when there's a whole web out there with various predictions that we can observe and so on and so forth, requires finding something that actually directly contradicts the idea of expansion. And I think that that's something that we're missing here. Like the plum pudding model, going back to atoms, the idea that the positive charge is uniformly distributed in an atom is directly contradicted by the fact that there is a non-uniform like rate of reflection. Like reflections only happen very, very rarely, and most of the time it just passes right through. That is a direct contradiction. Those two ideas cannot be like, there's no tweaking to the plum pudding model that you could do to fix that. So that experiment does away with the plum pudding model of the atom. And then we can look at, actually, the atom's a great example, right? Because initially the thought was that electrons like go around the nucleus like the planets. Mm-hmm. And then more data was discovered, and there was something called the Lamb shift that was discovered in the 30s, I want to say. And that was like, well, actually, if you assume that it just goes around in a circle, then you'd run into some problems, right? You'd have to explain why atoms are stable and things like that. So you tweak the idea. But the core idea that electrons in some sense orbit like a small nucleus that's positively charged, that core idea never stopped being right. Even though the explanation of how that works precisely was basically changed over the course of, say, 50 years from the 1900s to like the 1950s. The core idea never stopped being the model. It's just the exact mechanisms, the details changed. And I think that's fine. I think that's exactly what we expect to happen when we're talking about frontline physics, right?
Right. And see, that's why I hope, like, I would love to hear if you look more in depth into these, the observations of the galaxies, because I do think we have the contradiction with expansion, like a true contradiction. But I mean, I do have to admit that I am trusting in the data that's being given by, the scientists that are against the Big Bang. So, so like I can't myself know, which one is true, but I'm not hearing anything from the Big Bang believing side, that like is I'm hearing whispers from, I'm even hearing admissions from the Big Bang side that there's a problem with the galaxies. So, you know what I'm saying? Like, I would love to, because what the anti-Big Bang are saying, the scientists are saying, is that these galaxies are like below the minimum radius that a galaxy can possibly be, like according to the smaller expansion model. Yeah, like they're impossibly small and dense. Like they are impossibly massive, impossibly bright. Like one in particular is like 14,000 times the volume brightness of any galaxy in the local universe. So like 14,000 times, like hundreds of times, and like many of them are hundreds of times the surface brightness of any galaxy. They're like and below the minimum radius that a galaxy would need to exist. So, I mean, I can't know myself whether that data is correct. But they're getting the data straight off of the results, the data that's coming out from JWST. Mm-hmm. So as far as I can tell, they are correct. And I'd really like somebody who is an expert in the field or to look into it. So
I don't actually know anybody who works on JWST data analysis, and I don't think my one friend who's acquaintance who's an astrophysicist actually works with like ancient galaxy data, but I can ask her. But one thing that's interesting, and I don't think that you're relying on this, but this is something I've run into in the past, just for people who are listening, is there were those 6 galaxies, universe-breaking galaxies, that was all the hoopla a few weeks ago. Apparently, so again, a friend, I don't have the data hasn't been published. Or the data has been made publicly available yet. spectrograms haven't been done yet on those galaxies. So as far as I know, we're not even sure if they are galaxies. But more than that, and I think that was brought up in the debate, but more than that, somebody that I know actually got some of the data leaked and did an analysis himself. And again, I can't confirm this because I'm not him, and he just, but it sounds like from what he mentioned to me the other day, after he did the analysis, is that the paper that was written about them was using like the most optimistic, like the largest possible masses that they could have used, the furthest possible distance, the oldest possible star. So it seemed like they were being very optimistic as far as the analysis goes, perhaps for, I don't know, to get their name on a big discovery kind of thing. So like, I'm not claiming any academic dishonesty. This is just what my buddy has told me, but it sounds like that it may have been a little bit like the excitement may have been a little bit hasty. And this is something that we'll find out about in the next few weeks or months. We'll like more information will come out about this and so on. So, but it's just something to keep in mind. Like this data's new and subject to change. So,
well, do you think if it did come out that that these galaxies that we're observing, like, I mean, and I would like to know, because are you referring to the paper that we put up? I mean, I don't know.
I don't know if you guys put it up. It's the one. It's the one that was in Astrophysical Journal. Sorry, it's the one that was in Nature, I think.
Okay.
It was like
that one. Mm-hmm, that one isn't about the expansion issue. Like what I mean is like that one is about the formation of the galaxies, and like they're too massive to form at that time. So it's like one for the galaxy formation model. It's not
right.
You're not really talking that one. They're not talking. I read that one. They're not talking. They don't talk about the issue related to expansion in that one.
Right. So I just don't know and the only reason I bring that up is because the paper that you did bring up about the meta-analysis of the JWST data. Mm-hmm. I don't know if they included that data in their analysis, like the sizes and the age, the sizes and the distances, and the ages in their analysis. So like that's the kind of thing because they were using like in some cases. Well, I actually don't know if they use that data, but I just don't know if they were using like preliminary data that hasn't been vetted and things like that yet either. So I just can't comment on that. It's hard to say what. Because
they were using data that has they were using galaxies that have been spectroscopically analyzed.
Okay.
So,
okay.
Yeah. Mm-hmm.
Okay. Fair enough. That's fair. I didn't read the paper in its entirety, so that's fine.
Well, I would be interested if you did read the paper in its entirety, because I think if that data is correct, I think that is the absolute contradiction to the expansion model.
So I'm looking for. Do you remember what it was called? Because I had it up, but I can't. I have like 24 papers pulled up on my computer, so I don't remember what it's called.
I don't remember off the top of my head. I can get it for you. Hold on.
Yeah, sure. Oh, cosmological model test with JWST. Was it that one?
Possibly.
It's 27 pages. It came out December of last year.
That's the one.
Okay.
Yep.
Okay, so this one, this one's much newer. How did this get? When did the JWST data start coming out? Like in June?
Yeah, or July. Mm-hmm.
That's a really quick turnaround. Physics is much faster turnaround time as far as publication goes than it is in mathematics. So that's just a point of contention that I have. I'm mad about it, but it's neither here nor there. Large scale structure. That was something that we were going to talk about.
Yeah, sure.
So I looked into this, and I know you're going to hate it.
Okay.
Apparently, like I can't. It seems contentious as to whether or not there's actually a problem with the cosmological principle. Like whether or not these large scale structures go against the cosmological principle. I know that you brought up a paper in the debate that suggests that it was, but I found a few articles that say, well, actually, it's fine. So it's just hard to tell. Like there's a paper by Sam Christian. That's a very like standard name, Sam Christian, called "Re-examining the Evidence of the Hercules Corona Borealis Great Wall," which is the thing where the GRB ring was found, and where they talk about the statistical significance of these things. So this is all to say, I don't know if it's as compelling as it was made out to be.
Okay, well, I mean, look, I'm open to examining the evidence on both sides. Um, you know, but I'm basically like, I'm not sure why I would choose one paper over another if one is saying it does violate the cosmological principle and one says it
Right.
doesn't. I'd have to understand what their reasoning is,
Yep.
to know if that's really accurate.
Yeah. So, and I mean, like, unfortunately, like this is some, wait, is that like the one? No, it's not. The unfortunate thing is like some of these papers are even impenetrable for me because like this is like proper astrophysics or even astronomy stuff, which is, while related to what I do, it is a different field. Like physics and astronomy are different, closely related, but different. And so these kinds of, like, they talk about various like well-known statistical models that they use for these kinds of investigations. And I just don't, I haven't heard of those things before because that's like the jargon and the lingo in their field that I've never encountered. So it, like, honestly, like I was just looking at like the abstracts for these papers and taking a look at the introduction and conclusions. So like, it's really hard for me to actually even say what, like, for me to personally evaluate which which paper is more trustworthy than which one,
Yeah.
And I understand like that's a totally, like, I understand that you're having the same issue, and that's why I would just go and ask an astrophysicist.
Right. But which one? An anti-Big Bang astrophysicist?
Well, I would just go ask the astrophysicist that I know, like the one that's my friend. Because I don't know, like, I mean, you could just you could just like pull up a list of like, list all of the astrophysicists in the world in an Excel spreadsheet, randomize it, and then just email the first one. But, how do you, like, I don't know, it just seems like that's not a good method of figuring out who to listen to, right?
Right. Well, I think overall for me, like when I look at like all the things that are required, like that's something I want to ask you is like all of these hypothetical entities that are needed, the free parameters that are needed to keep the Big Bang afloat. Like, do you really think the evidence like is enough with the cosmic background radiation to like keep this whole thing floating with all the free parameters?
Isn't there only one free parameter, and that's the cosmological constant?
No, there's so many free parameters like that. And actually, I can send you a paper by an astrophysicist. His name is Michael Disney. Actually, you can just Google it if you want. But sure. He wrote a letter called like something like Big Bang Science or Folktale. And basically, he talks about all the free parameters that are inserted now in the Big Bang. And this was the original thing that I read that caused me to say, oh my gosh, the Big Bang is just like, oh, it's on nothing. Like it has nothing. But this is just
So for what it's worth, like that article's not a paper. Yeah. It's just like it's like a Scientific American or American Scientist article. But sure. I pulled it up.
I mean, basically, he published that and then he retired. Okay,
fair.
So, I mean, I shouldn't say published. He put it out. Okay.
Yeah.
He put it out, but if you read it, he kind of goes through like all the free parameters that are inserted. He has a little chart in there, and I don't really understand how this is done, but he had like significance calculations for like, all the many free parameters that are needed. And he says that's the problem with the Big Bang is that like, so many the number of free parameters greatly exceeds the number of observations. And that is not healthy in any, it's not healthy and it's not normal for a scientific theory.
So like, and I'll have to go look into this, but like my understanding is that like one of the reasons why, and again, I could be completely wrong here because this is based off of like stuff I learned in grad school and not like actual research that I've conducted on the matter. But and when I say research, I mean like it's not my area. is the reason why, for example, we detect why there is like a disagreement in like lithium abundance is because the Big Bang nucleosynthesis is pretty much fixed. Like it's just fixed by standard model, not standard model cosmology, standard model particle physics for nucleosynthesis, for example. And yet he's listing this as like as Big Bang nucleosynthesis having a free parameter. So it just seems like it's, and I don't know it. I'll have to look into what it's saying,
yeah.
but it just seems like there's more listed here than would be needed.
Well, I think the reason he is doing that, and I could be wrong because I am definitely not an expert on this, but the reason is because there's an assumption that we could even like that have the antimatter and the matter that like the observations that we do when we like do stuff, in the like particle accelerator and stuff, is that we create matter and antimatter. So there has to be something that causes matter to win out over the antimatter.
Mm-hmm. And right, but that's not a cosmology problem, I don't think.
We have to assume, right, that can happen. So that's a free parameter. Because that actually contradicts our observations. Because when we do the observations in the particle accelerator, it's, antimatter and matter. So we've got to have a way, like, it defies our observations to say that matter can win out over antimatter.
Well, so there's no mechanism to account for the matter-antimatter disparity, but that's just the reason why that feels like there's an assumption added in is because the original assumption is that there was the same amount of matter and antimatter created to begin with, which that's an assumption that we shouldn't necessarily grant, right? So like the problem of matter-antimatter imbalance isn't necessarily a problem at all, right? It could just be that however our universe got here, whatever caused it, that there was more matter than antimatter in the early stages of the universe for whatever reason that we don't know. And it's not necessarily the case that it started out balanced and then it got unbalanced for some reason. It may have just started out unbalanced. And that's not like, it would be surprising if that were true because it would seem kind of ad hoc, but we can't discount that as a possibility. So it just seems like I don't know if that's a free parameter. Like that's just based off of observations. We just know that there's this much matter and this much antimatter, so we plug that into our equations, right? It seems like that's actually fixed. Like it has to be fixed, and it would be used as an input, not a free variable.
Well, except for the problem that right now we've got 95% of the universe being like dark matter and dark energy, right? So like what I mean is like things don't work out with our calculations if we just take the baryonic matter.
Right. So first, do you have a problem with dark matter, or is that like not really?
Okay, I don't care about it, but I do have a problem with it in that, I was saying in the debate, and this came up in the question and answer time. I was like, like, I agree with you that it's a red herring. Like, it doesn't really matter if dark matter or dark energy. It doesn't matter for the Big Bang Theory,
right.
Except that the Big Bang Theory is assuming dark matter, which I think is a problem because we haven't detected it. And so, yes, it's convenient for our observations. But like I told the guys, I could just as easily say that it's dark fairies. And there's no way to falsify that, right? Because like in the same way that there's currently no way to falsify dark matter because we build machines, it doesn't show up. But instead of saying like, okay, well, maybe there isn't dark matter, we say, well, maybe we just can't detect it. And so I could insert dark fairies just as easily and say, well, you can't detect the dark fairies. It's actually dark fairies doing these things, right? Like that's the problem I have with dark matter is that it assumes, like we're assuming it's there because it helps fix the issues, but we don't actually know what it is.
Yeah, we certainly don't know what it is. And if dark fairies like have the same mass as the dark matter particles or whatever, then sure, they're dark fairies. I don't care. It doesn't matter to me. But like we know that there's something there doing some sort of gravitating and we don't know. Maybe it's tiny black holes. Maybe it's some sort of subatomic particle that we've never seen before. Maybe it's something else. But there's something there, right? I just don't know if we agree that that's the case.
There's something causing the phenomenon, but I'm not ready to say that it's dark matter. It might be a misunderstanding on our part of how Newton's laws work at that scale, or, what I'm saying is I would prefer to leave open other options, like without like assuming the dark matter.
So I mean, in a sense, you are right that like a lot of this is scaffolded on top of each other. In that you have like when I say that there's one free parameter for the lambda CDM model, what I mean is that, well, we know how much baryonic matter there is. We can just see it. We can count it. Mm-hmm. So that's not a free parameter. We know how much and if we know how much dark matter there is, which I claim that it's something that we can measure, then if you tune the cosmological constant, that fixes the ratio between dark energy, dark matter, and baryonic matter. And so that would be a free parameter, certainly. And so you could, if your cosmological constant was bigger, you'd have a bigger proportion of dark energy. If it was smaller, you'd have a smaller proportion of dark energy. And in that sense, that's a free parameter, certainly. And we fix that with the data. But my claim is that the dark matter, I mean, and I did some reading on this because I was making a video on it. Again, super useful way to learn is force yourself to make videos on things that you don't know about. Like the alternative is, yes, you could come up with some sort of alternative that does away with dark matter, but there's like, and this is was this brought up in the debate, the bullet cluster? Was that brought up at all?
I don't remember, because I've had several conversations since then,
sure.
So I don't remember. Yeah,
it's the so-called smoking gun for dark matter, namely. No, this was brought up in the debate, but I just don't think that whoever brought it up was the name. But it's the whole thing where you have two galaxies colliding, and the gas slowed down in between, but the gravitating mass didn't. And that to me, like I've thought a lot about this, because like I work in gravity, and so like different ways of explaining gravitation is like really exciting. There was a paper that came out in September about something like a variation on Einstein's field equations, which is super exciting because it claimed to explain dark matter. It claimed to reproduce the galaxy rotation curves without needing extra matter. But then you run the calculations, and this is something I actually did. These are actually calculations I can do. So I ran the calculations myself. I emailed the author and I'm like, hey, there's something wrong here. And you can test it on things like the bullet cluster, and it just falls apart. Like, it doesn't work. And so this is, again, one of those things where our best current explanation is dark matter. And every other attempted explanation that we've come up with fails for one reason or another. Now, that doesn't mean that dark matter is the thing that's actually there. There might be some better explanation, but we just don't know of a better one yet. And this one seems to make good predictions, which is why I'm comfortable saying, yes, assume that the dark matter is there, and then we can use that in the next step in the ladder. Now, yes, if dark matter is not there, then general relativity is out the window. And if general relativity is out the window, then the Big Bang is surely out the window. And like the scaffold falls apart. But science is kind of scaffolding to begin with. Like, if Newton's laws are out the window, then the whole thing goes away, right?
Mm.
So we have to trust on the previous steps, I guess, is what I'm getting at.
Yeah. Okay. Well, I mean, and that's our focus in the debate, was really to hit at the base of the Big Bang model, which is expansion, and show that expansion is, if expansion is not happening, then that's where the Big Bang completely goes away.
I mean, that's certainly true. I mean,
so that's the base of the scaffolding. So to me, I feel like we gave evidence against expansion. I don't feel like any evidence has been given for expansion. So I don't if what's in question is the redshift, we are saying there's an alternative explanation for the redshift. So, the redshift, is there any other evidence besides the redshift, since that's what's in question? Is there other evidence for expansion? And, I mean, like, I think the evidence is really not there.
I mean, and so we're going to end up circling again, unfortunately. But like,
CMB. Mm-hmm.
Yeah. So no, I wasn't going to say the CMB. No, I was just going to say like, look, like and this is something that's completely unrelated. I do this thing. Never mind. I'm not going to bring that up. Somebody asked me to read a paper a while ago, because they were questioning the Big Bang too. And they're like, hey, go read this paper about tired light. This was like 3 or 4 months ago, so it was completely unrelated to this. But I read about tired light and I looked into it because I hadn't heard about it before. And it's like, there are a lot of problems with it. It has a lot to explain and a lot of pitfall. And so as an example, the same kinds of things the same kind of problems that you have with like the Big Bang model, where like, oh, you run into a problem, you tweak it a little bit to fix it. Right. I feel like the tired light model does that, and it makes fewer predictions while doing so. So like, if it were the case that the Big Bang model didn't actually like have explanatory power, because like whether you think it's true, like if it is true, it explains a lot of phenomenon. It has high explanatory power. If it were the case that the Big Bang didn't have high explanatory power, and we still had to tweak it a lot to get it to match predictions, then it might be reasonably called like just like a bad model, and we should go back to the drawing board. And tired light to me feels that way. That like it's like a really ad hoc model, and it doesn't have a whole lot of explanatory power. Like it's a model built specifically to explain this one thing, and it doesn't explain anything else. So to me, it seems like the tired light model is just like just on like philosophical grounds. It just seems like a weaker model because it makes fewer predictions and requires the same amount of tweaking. So I would just say it's like, you say that there is an alternative explanation. The alternative explanation is just garbage.
Yeah. Well, but what if the expansion is garbage too? That's what I'm saying. Like, how about throwing both out? If tired light is really garbage and expansion is really garbage, how about throwing both out and saying, okay, let's figure this out, and so
that, I mean, it's a good question, right? So what are we to do as scientists, myself included, even though I don't work in this area? What are we to do when we have data that is predicted by some models, but it's not entirely correct, right? Like, the go-to one is lithium abundance, right? What are we to so if we have a model that's not entirely correct, should we discount the entirety of the model and throw away its usefulness? Because I mean, like, say what you want about the Big Bang, like at least it does make some predictions that are like useful, right? Like we can use them to figure out how far away galaxies are, because like the relationship seems to be at least for nearby galaxies, because like we can verify those with other things, right? So like there are certain things about our universe that are like well explained by the Big Bang, and so we can use those to like learn about the world around us in an indirect way. Should we throw away that useful power of the Big Bang, even if it's at the end of the day like fundamentally wrong? Should we throw that away?
But I haven't seen how it is useful, though, because our observations are independent of the Big Bang. What I mean is, like, okay, our standard candle observations of distant galaxies and stuff, those are good without the Big Bang. And so, like, the observations that we're actually making, I don't see how the Big Bang is useful to them.
Well, I suppose okay, no, you're right on that. Like, it just seems misguided to me to say, look, we know that like there is something wrong with this model, and so we should just not consider it at all and go completely back to the drawing board, throw away even the idea, not just like the specific details, and start again. Like, this makes me think of general relativity, right? We know general relativity has problems. Black holes, Big Bang, right? General relativity has problems. Namely, it's not like it doesn't play well with quantum mechanics. But does that mean that we should throw away general relativity? No, of course not. General relativity is remarkably useful for predicting the world around us. Like it explains why Mercury has the orbit that it does, for example. So I think it would be a mistake just from a sociological perspective to just say, look, we should just do away with all of general relativity because we know that it can't agree with quantum mechanics. We should just start over from the drawing. I just think that, like, just from a sociological perspective, it's just not it's not an effective way to do science.
But what is the Big Bang doing for us right now? Like, what are the good things that it's doing?
I mean, it has explanatory power, right? It explains, like, why we see it purports to explain why we see certain things. Just like how general relativity explains why Mercury precesses around the sun in a certain way.
What is the Big Bang show? Like, what are the things that
it explains why there's expansion, why there's a CMB, why, I didn't bring this up because I don't know a lot about it, but I know that there's something called baryonic acoustic resonances. It explains, various, so a scientific model is only as good as its explanatory power, right? So a model that just says this is just how it is not a particularly useful model because it doesn't explain why anything is the way it is, right? So and maybe this is just a disagreement on how science should be done. But, like, to me, science is about providing explanation for the way the world is, for the way the universe is. And so general relativity does that. The Big Bang model does that. Quantum mechanics does that. Atomic theory does that. All of these things, they provide explanatory power and they explain why things are the way they are, even though we don't know that any of those are true for certain. But we know, like Newton's laws, right? Newton's laws provide explanation as to why things fall at the same rate. Even though we know Newton's laws are wrong, they're still useful. It's still a useful model for understanding the world around us. So it seems like that the explanatory benefit is, like, there is explanatory benefit. It gives us ideas as to, why the universe is shaped the way it is, for example. So
yeah, but I guess, like, I'm agreeing with you that general relativity helps us, that quantum mechanics helps us, Newton helps us, even though there's, limits to what we understand with regard to those, and they might be wrong in some ways. But I'm still failing to see how the Big Bang has explanatory power. Like, the only thing that I could say is, okay, it could be an explanation for the CMB. But how does that really help us? Like, what is the Big Bang doing for us? Like, where is the power?
So the power is so we have observations, right? We just detect things doing things in our universe. And the question is why do they do those things? And the goal of science is to answer that question of why. And so we see light, we see galaxies redshifted. We see or better yet, we see supernova appearing redder than we think they should be. Why is that? Well, we could just say, I don't know, and then just move on with our lives. But then the scientists wouldn't be very good scientists, because the goal of a scientist is to answer that question, why? And so we have an explanation as to why. And then we can go check it if that explanation comports with other questions that we have. And even if you disagree with all of them, it certainly has explanatory power for some of them. It does explain it. Well, this same and this is what makes a good scientific model, right? If one idea can explain a whole bunch of different things, that's a good model. That's the kind of thing that we want. It might be true that, let's just say, okay, so we know general relativity breaks down at, like, black holes, let's say. Maybe it doesn't, but let's just say it does. Well, maybe the Big Bang just doesn't work, up to a billion years, or up to 12 billion. Maybe it works perfectly up to 12 billion years ago, and then it stops working for whatever reason. Well, we'd still have explanatory power as to why redshift happens, because the universe is expanding and has been expanding for 12 billion years. Maybe it breaks down for some reason before that, but there's still explanatory power.
But, I mean, right now, like, what I'm saying is it's a wrong explanation. Like, it may be an explanation, but if it's a wrong explanation, then it doesn't have explanatory power.
It's hard to tell if it's
lying.
so it's hard to tell. I see the point. It's hard to tell if. So, going back to the atom, the idea of a small dense nucleus surrounded by electrons was the right core of an idea. But if you told someone at that time about the Lamb shift, which is a hilariously named quantum phenomenon, if you told someone in the 1910s, I guess, that this happened, they would say, well, then your model makes wrong predictions. But that doesn't mean that the model itself was wrong. It just means that the details of the model are wrong. And so I think that we have to figure out a way, and maybe this is just something to think about. Like maybe we just, like as scientists, this is something we have to think about. How do we distinguish between when the core idea of a model is wrong and when the minutia, the details of a model are wrong? Because my fundamental claim, and I think this is where we fundamentally disagree, is that I think that these disagreements between the current Big Bang model, the lambda CDM model, and what we observe about early universes or lithium, things like that, I think that that's an issue with either external factors, external models coming in and interacting, or maybe some of the details that we have of the Big Bang are incorrect. But it seems like you're on the other side of the coin, where you just think that this means that the whole idea has to go out, like the core concept. And I think that, I mean, I don't think we're going to come to a conclusion on that tonight. I guess it's midday for you, but I don't know if there's a good way of telling when that happens. Of like,
yeah, I mean,
how you decide.
I mean, for me, I guess, like, I do think that expansion is the base. And so, like, there can be other wrong predictions, and those are important, but they're not like the nail in the coffin. But like, if the universe is not expanding, then that's when it's time to get rid of the theory. Like, you know, because that's the whole basis. So
yeah, well, yeah. So I mean, then it sounds like what needs to be come up with is some other way to test if there's expansion, some independent way that doesn't rely on redshift. I don't know if I'm sure other people have thought about this before. I don't know if other people have written about this, if people have done these tests. I haven't read too much about it. So like, it's something to look into, certainly. But we have to think about what would it mean for there to be some other way of detecting expansion aside from redshift. How else would you detect it?
Well,
and,
I mean,
it's a hard question. I don't know the answer.
I mean, this could be totally wrong, but I mean, like, if the universe is really expanding and it's expanding as fast as they say it's expanding, I feel like, 50 years ago, we could have, like, marked the redshift of a galaxy, and then, like, in 100 years, it should be in a different place, right? Like, it should have a different redshift.
I think that I think that the scales are too big. I think that you'd have to measure it over millions of years rather than like decades or maybe 100 years. I would think.
If that's true, then okay, my experiment fails. But I mean, what I mean is, like, right now, I feel like there is mounting evidence against expansion, and it does have to do with these galaxies. But I would, like, I don't want to trouble you at all. Like, this has actually been a really, really great conversation.
It's not a trouble. It's not trouble.
I have loved this. But I mean, if you're interested in pursuing this further, like, I think the place to start is with that, reading that paper, with the galaxy observations, the one that came out in December, and like talking through that to see, does it really get to the conclusion, is the data good? Is there anything wrong with the data? Because to me, it's a good evidence against expansion.
So I'll take a look at it. The only trouble is that I have a feeling that there will be some things in there that I just am not like, that I just don't know about. Like, I don't know all of the statistical methods that they use in astrophysics or in astronomy to do this sort of analysis. So I don't I will read it. I don't know how much I'll get out of it. We can talk over messages or whatever. Are you on TikTok often enough that you'll see messages occasionally?
I'll check it if I know that you're going to message me. Yeah, I'm new to TikTok, so this is
if there's an email or something, we can email back and forth. If that'd be better.
Yeah.
Okay. I'll send you my email on. I'll message you my email then, and we can communicate via email. That's fine.
Awesome. Well, thank you so much for your time. I mean, did you have anything else you wanted to talk about?
I don't think so. I mean, like, we could talk about religious stuff, but maybe we save that for another time.
Yeah, I would love to talk about religious stuff. That would
if you have time now, that's fine with me. But I actually promised my wife I'd watch a movie with her, so I actually probably shouldn't now.
Okay. Yeah, we'll do it another time.
All right, sounds good. Well, thank you for being here. I do appreciate it. It was a delight, and I guess thank you. I don't know if Danny's still here. He was here earlier, but yeah, thank you
Yeah.
to Danny for setting this up because this was really good.
I know. Okay. Thank you, Blitz.
Of
Nice
course,
to
of
meet
course.
you.
Take care.
All right.
Likewise.
Bye-bye.
So that was delightful. I mean, like we disagree, but I think it was still like a fun conversation. And I hope some of you guys got something out of it. For what it's worth, this is my alt account because my main account is still banned and will be banned for another 3 days, or temporarily suspended anyway. Let me check in with my wife really quick. All right, so why am I suspended? Because somebody religious reported me when I was questioning the existence of God. Right, so I'm going to do Ask a Physicist for like half an hour or so, just because I feel like I haven't done one in a while, and I know that you guys like that. So let me just change the background really quick. This one? Nope, not that one. Nope. Found it. Excellent. We can just wait until you get your no. So no. This is fine. I don't, Misty. I don't know how long you have. But I actually kind of wanted to do an Ask a Physicist for maybe half an hour or so, and then I'm gonna go watch a movie with my wife. Yeah, I'll take questions. There's 100 or less than 100 of you guys, but I'll take questions. Why do stars bob up and down in a galactic orbit? For the same reason that roughly the same reason that a spring oscillates up and down. There are forces present. In particular, what a star. Let's say here's the galaxy center and here's a star. A star feels a force this way, so it's going to feel a force. It's going to feel a force inwards, and that's going to cause it to orbit. But it's also going to feel a component that's downwards, and so it'll be pulled downward. And then once it gets down here, it'll have a force that's upwards, and it'll just go up and down like that. Alistair Riddick on Quora, can you give it a glance to see what you think? Wait, sorry. What was that about? See? Did gravitational waves that were detected by LIGO in 2015 prove gravity? Yeah, pretty much. I mean, gravity is real. That wasn't the first proof of gravity. The first proof of gravity was Cavendish in the 1700s. But yeah, I mean, like this is pretty nail in the coffin for thank you for gravity. Sorry, just gonna drink some water. Alistair Riddoch, Quora. Studied philosophy and ethics. This this looks like the ramblings of a madman. Not gonna lie, it looks like the ramblings of a madman. Or somebody who doesn't know what they're talking about anyway. Would I weigh less in a dark room versus a room with light in it? No. How do you think gravity and quantum will be made to coexist? I don't know. If I knew the answer, I would, have a Nobel Prize. A little bit, honestly, I work with this guy. He's very informal, but it's interesting. I'm just looking at the diagrams. Like, infinity times jiggly ball plus motion equals one universe. It just seems like it's wrong. That's all. He's looking for a physicist to look over his work to work with to refine his idea. Yeah. So I do this, by the way. I will. This is called rent a physicist. It's a thing that I do, and I charge $100 an hour. So if he wants to, if he wants to rent me, I will. He can. I'm glad to have him. Are the poles shifting? Yeah, it seems to be regularly a thing that happens. The poles do shift every 12,000 years, I want to say. SETI is listening for the structured signals in a sea of gravitational lens noise. Yeah, no, that's exactly what SETI's doing. Does the overall mass of a galaxy determine the shape of a galaxy? Or does the black holes in the center play more role? So the black hole might play a role in galaxy formation, but the black hole makes up like less than 1%. I think less than 1% of a lot of galaxies' mass. Do you have a qualm with rejecting statistical independence? Well, that just implies superdeterminism. So, I mean, if you reject statistical independence of like the Bell experiments, then yeah, you're just implying superdeterminism. And I just don't like it. It seems philosophically gross to me, but like in principle, I suppose it's plausible. How do we know exactly how the poles shift? I'm not a geologist, but I'm pretty sure that you can measure like historic magnetic fields in like old iron and stuff, and you can see that they pointed in different directions. What are the consequences of the poles shifting? I don't think that there's a huge consequence, actually. Wait, what? The poles will shift? Can you explain more? Yeah. So the magnetic poles shift. You're really expensive, but it's justified. I have a PhD. Of course, I'm expensive. You want to hire a physicist? It's gonna be pricey. Also, it filters out people who don't like who aren't serious, right? Hey, physicist, I have a question. How are you doing? I'm doing okay. Iron filings deposit in riverbeds and deltas. There you go. There's your answer. Thank you, Chaos. See, this is why you're useful, because you answer questions I don't know the answer to. Almost just died. I'm good. It's a very debatable subject if I'm useful. I don't know. You seem useful. Both my cats are on desks and countertops because they're being very cute. It basically changes where it's super cold. No. This is not the axis of rotation. These are the magnetic poles, not the axial poles. These are very different things. Don't ask a physicist anything that's not either basic physics or his field of study. I mean, no, you can ask me more stuff that's not basic. Like, I could answer at a master's degree level basically anything in quantum field theory, quantum mechanics, general relativity, cosmology. Condensed matter I know nothing about because I just don't care to answer it. And so like that's much more than basic physics. Blitz, did you just drink heavy water? I hope not. Heavy water is poisonous if you drink enough of it. Rothschilds manipulate the weather, nothing else. Really? That's a weird thing to say, but okay. JSTE I don't know what that means. Well, if you guys don't have questions, I guess I'll end it here, unless, you got questions for me. Sorry, still coughing from that. Any good books for a newbie? A Brief History of Time is excellent. What makes atoms slow down to below light speed? They were never faster. They were never at light speed. So I don't know what you mean by slow down. Was it good life? I like to think so. I thought it was very productive. Where do they pay $100 an hour to PhDs for consulting work? Well, Sabian Hosenfelder charges $150 an hour. So I think I'm worth at least 2/3 of her. Why does number 42 show up so much in science fiction? Wait, Douglas Adams. Yeah, no, it's Douglas Adams. That's why. Did you ever consider experimental physics? I did experimental physics as an undergrad. I worked in medium energy particle physics, which is a very specific branch. What resources did you use during your undergrad and master's? So, I mean, I did a master's as it was like a master's PhD program. So I got my master's after 2 years, but in the program. But what resources did I use? Google. That's really it. And the textbooks, I guess. Why is there different shape of galaxies? I actually don't think that that's known. I know that spherical galaxies are more likely to form after a collision, but I don't know if it's actually known why some galaxies are spiral and some are ellipsoidal. What's vacuum decay? So vacuum decay is a, oh, just I missed your question. Sorry. Where's your question? Ask it again. I promise I'll answer it. Vacuum decay is any sort of process where you have a system that's metastable, meaning that like maybe the Higgs boson or the Higgs field, while we think it's stable, it's not actually stable. It's like it's at like a local minimum, but there's like a much lower minimum elsewhere. And so vacuum decay is basically what would happen if the Higgs field quantumly tunneled to the actual proper minimum. The vacuum would decay because the Higgs field fills the vacuum. Is HARP real along with CERN? They're both real things. Yeah. What's your favorite topic to debate? It really depends on my mood. Sometimes I like politics, but sometimes I'm really not in the mood for it. Sometimes I really like theology. So I actually like all of them a lot. Will a sun rise from the west in the future? And if that happened, how would it affect us? I don't see why it would. That has nothing to do with the poles shifting, by the way. Do you think you're more intelligent than Sheldon Cooper? If he was real, if he was real, he's like an autistic savant. So no, I'm not more intelligent than him. What was your thesis about specifically? 1 minute version. So it was basically about characterizing. It was on conformal hypersurface geometry. So what that means is there are certain mathematical structures that show up in physics quite frequently, where basically you have a space, and it's not like 3-dimensional space; it might be higher dimensional, and that space has a boundary. So think like the edge of a ball is a sphere. So the sphere is the boundary of a ball. And so there are certain types of like mathematical structures you can put on these spaces. One of them is called a conformal structure, where basically the geometry is the set of all possible ways that you can stretch and shrink and twist that whole thing. I guess not twist. I guess just stretch and shrink. And so my thesis was on investigating geometric quantities that don't change when you do that when there's a boundary. Does the magnetic poles shift without reason, or that's a question for chaos. Is there Higgs fields in Earth's atmosphere? There's Higgs fields everywhere. Do you think the big collapse and bounce could happen, and therefore the universe is in a loop? It looks like it doesn't look like there's going to be a collapse anytime in the near future. Enjoy the movie. Take care, Misty. Does the Higgs field comprise of particles, fields, or both? The Higgs field is a field. Is the Big Bang Theory shows physics accurate? Sometimes, yeah. Does it bother you how much people talk about quantum mechanics and are completely wrong? Sometimes, yeah, unfortunately. What is an easy physics experiment to do in home conditions? Build a cloud chamber. You can build a cloud chamber with some dry ice, some isopropyl alcohol, and some like a plexiglass container, and it's super, super cool. You can detect radiation with it. How do you think the universe would end? Not with a bang, but with a whimper. A cold heat death. Are you scared about the new developments in AI? No? I didn't ask if it was in the near future, though. Of course, the universe is expanding. Yeah, no. The universe seems to be accelerating in its expansion, though, which means that it's not going to slow down, but it'll keep speeding up. Got it. I hate that my alt account doesn't get sent through the algorithm as much, because it means that I don't get as many questions, which is really a bummer. Would it keep expanding without limit? It seems to be the case if you accept expansion. Again, I know that there might be some people who don't. Speeding up to what effect? It's the expansion is the accelerate. So the rate. So A of t describes the scale parameter of the universe, the scale factor of the universe, how big it is. The derivative of A of t tells you how fast it's expanding. The second derivative tells you how fast the expansion is changing. And two derivatives of A of t seems to be greater than 0, which means that it's accelerating. Physics is fun. You just create stuff because it might explain something, then you try to find it. Yeah, exactly. What's your favorite thing to study outside physics? Math. Time is not moving faster now. It was always the same. What about black holes? Won't they just take all matter and energy to singularity again? If there were enough black holes, yes, that is what would happen, but there don't seem to be enough black holes to make the universe recollapse. They would just get further and further away from each other forever, unfortunately. Or fortunately, depending on your perspective, I suppose. Are chemistry and physics actually that similar? I've never studied chemistry, so I don't know, but I imagine that physical chemistry is basically just physics with less or with more atoms. course, there's Hawkins addition radiation, though. Exactly. What's the hardest section you studied in physics? Topological quantum field theory was hard. Off topic, I joined late. Did you ask her to explain why she has a bias against the Big Bang? She has a bias. So she's a young Earth creationist, so that's why she has a bias against the Big Bang. But that's not what we were there to talk about. We need more mathematicians and physicists in biology and biomedical sciences. Interested? No, not for me. What is a singularity? A singularity, at least in general relativity, is any place or moment